Okay, Assalamualaikum wabarakatuh and good afternoon to everyone. Okay, today we're gonna continue our class session, part 2 of graph theory. So we're gonna learn until graph terminology and special types of graph and representing graph and graph isomorphism. Okay, this is a section. We're gonna learn about adjacency list, neighbor list, adjacency matrix, incident matrix based on the edge, adjacency based on the node itself or vertex, incidence is based on the edge, and isomorphism of a graph. So, what is the incident matrix? So, most useful when information about edges is more desirable than information about vertices. So this is the incident matrix based on the edges. You can see here based on the edges. And the adjacency matrix on neighbor vertex, most useful for information about the vertices, is more desirable than information about the edges. So remember, you learned about the graph theory before the mid-semester break. You have edges, you have vertex. You have vertex 1, vertex 2, and you have edges E1. Just to recall you, okay? And most useful, if you want to use incident matrix, the edges are more useful. If you want to use the adjacency matrix, the vertices or the vertex is more useful. These two representations are also most popular since information about the vertices is often more desirable than the edge in most applications. Okay, usually the information about vertices or vertex or node is more desirable than the edges or the path. Okay, so first, before we go into metric, we're going to build up the adjacency list. An adjacency list can be used to represent a graph with no multiple edges by specifying the vertices that are adjacent to each other. Vertex of the graph. So let's say you have this graph and you have 1, 2, 3, 4, 5 vertices. So what's the adjacent vertices for A? Is easily you can spot B, C, and E. Okay. What is the neighbors of A? B, C, and E. And so on. B is A, and C, A, D, E, A, D, and E. Okay. So this pretty straightforward. And you have your adjacency of a directed graph. So you have this is the undirected graph. Remember, undirected graph you can go both way. Is it me breaking up? Wait, not supposed to be. Is it breaking up? Okay, I'll try to repeat. So the adjacency list can be used to represent a graph with no multiple edges. Okay, this the adjacent vertices or the neighbors vertices. So if you have A, delete first this one. If you have the node A or vertex A, what is the neighbors of vertex A? Vertex B, vertex C, and vertex E. Okay, B, C, and E. What is the neighbors of vertex B? So you have A only. B is A. C is D, E, and A. So this is the neighbors vertex or adjacent vertex. Adjacent vertex. Still lagging out. Wait. Okay, anyone, can you hear me? Can you hear my voice? Is it breaking up? Okay, sure. Yeah. Okay. So again, the adjacency list or neighbors, okay, adjacent vertices or neighbors vertices. Let's say you have you have a node A. The neighbors of node A is vertex B and vertex C and vertex E. These are neighbors of A. Neighbors of A. Let's say you have vertex B. What is a vertex B? B is only A. Let's say you have a vertex C. The neighbors of vertex C is A, D, and E. Okay? Neighbors of vertex C is D, E, and A. And it's similar with the directed graph here. So what is the initial vertex A? The terminal vertex is B, C, D, and E. How about B? B and D. So you see, like, the only difference in the directed graph is we take example of vertex B here. We take the example of vertex B here. Since B only terminate at B and D, so the terminal vertices or the adjacency list for B is only B and D. It's not A or E because it terminates at B and this one is terminate at B. A terminate at B and E also terminate at B. So the terminal or the adjacency list for directed graph is different. It based on the which vertex it terminate or endpoint. So for the undirected graph, it's just pretty straightforward for the neighbor list or adjacency list. But for the directed graph, you must see where does it terminate. Again, I will show you like B here. B, you have B and D. Why? Because B and D, it terminates at D, and then again it's terminate at B. It's not A or E because it terminates at B and this one is terminate at B as well for A and E. So the adjacency list for B is only B and D, not A or E, due to the termination point. So this is adjacency list. So again, this is the pretty straightforward for directed graph. For U, you have V and W, V, W, and W, you have U, V. Okay. So now we learn about the adjacency matrix. So the definition, suppose that the graph with the set of vertices and set of edges is a simple graph where vertices, the number of vertices is n. Arbitrarily list the vertices of G as V1, V2, and Vn. So the adjacency matrix of AG of G with respect to the listing of vertices is the n times n01 matrix with 1 as I and j. So I and j is the metric. So this one A I J. If you AI1 J1, AI2 J, AI1 J2, AI3 J, AI1 J3, something like that. This is a matrix. When V1 and Vj are adjacent, as it's Ij the entry where they are not adjacent. Just don't worry about the definition. Later we'll go to the example. So in other words, if the graph adjacency matrix is Ag, Aij, then if there is an H between Vi and Vj, so the value of matrix is 1. And if it doesn't have an H from V1 to Vj, is 0. So we'll see the example here. So this is the undirected simple graph. So you have here, if you want to draw a matrix, this one you saw A, B, C, and D. This one is A, B, C, and D. So from A to A, there is no from A to A, so it's 0. It doesn't have loop. From A to B, it has one H, so you put 1. A to C, 1H, yes. A to D, also 1H. So you settle the first row. So the second row, B. B to A, yes, 1. B to B, no, no loop. B to C is 1, and B to D is 0. CA, there's a H to A, there's a H to B, there's no loop C, and there's no H to D. So this is the how do you generate the adjacency matrix. Okay, so the ordering of vertices is A, B, C, and D. A, B, C, and D, and this is A, B, C, and D. And this one, if you look on the second graph, A, B, D, and C, so you have here A, B, C, and D, A, B, C, and D. So from A to A, there's no loop, so A 0. A to B is 1, A to C is 1, A to D, there's no HA, so you put 0, and so on. So the adjacency of simple graph is symmetric is Aij is equal to Aji. What does that mean? So like Aij is equal to Aji. Let's say A12 is equal to A21. If you see this, this is A11, A1, A12, sorry. Let's check again. A11, A12. This is A12. A21 is here. A21. So this is considered a graph is symmetric. Let's say A13, A14, and A41. So A14 and A41 is the same, so it's considered a symmetric. Let's see this graph A11, A12, A21. This one is A21, A22, A23, A24, A42 is 1, A42 is 1. So this is also a symmetric graph. The adjacency of a simple graph. Remember, a simple graph. Why is a simple graph? Doesn't have a multiple edges, doesn't have a loop, and so on. So adjacency of a simple graph must be a symmetric, which is Aij is equal to Aji, meaning that A12 is equal to A21, A13 equal to A31, and so on. Also, since there are no loops, each diagonal entry ai for I2 and 3 is 0. Okay, A11, A11, A22, A33 is all 0. We check here, A11, A22, A33, A44, all 0 here. Is it okay my handwriting, or you need me to erase that? So just the entry of A11, A22, A11, A22, A33, A44, and so on is 0. Since there are no loops, each diagonal entry. So this is also a diagonal. Alright, thank you very much. Okay, next. Adjacency matrix can also be used to represent graph with loops and multiple edges. When you have a graph with loops and multiple edges, meaning it is not a simple graph. So by looking at the metric itself, you can determine whether this is a simple graph or not. Okay, by looking at the matrix, these the rules. Symmetric is Aij is equal to Aji, and each diagonal entry Aii or Ajj is 0. So when you have a loops and multiple edges, it is not a simple graph. A loop at the vertex Vi is represented by a1 at the ij position of the matrix. Okay, 1. So like A to A is 1. You have vertices here, A, and then you have a loop. So this value is 1. If you do a metric, this is A, this is A. So the value is 1. When multiple edges connect the same pair of vertices Vi and Vj, or multiple loops are represented as the same vertex, the adjacency equals the number of edges connecting to the pair of vertices. Okay, look at this example. We give the adjacency matrix of the pseudograph shown here using the ordering vertices A, B, C, and D. So A, B, C, and D. A, B, C, and D. A to A, 0. A to B, you have 3 edges. A to C, you have 0 edges. And A to D, you have 2 edges, and so on. B to A, you have 3. B to B, 0. B to C, 1. B to D, 1. C to A, you have 0. C to B, you have 1. C to C, you have 1. And C to D, you have 2. DA, you have 2. D to B, you have 1. D to C, you have 2. And D to D, you have 0. 0, 3, 0, 2. Sorry. Yeah, this better. Sorry again. Yeah, A, B, C, and D. A, B, C, and D. So A to A, you have 0. A to B, you have 3 edges, and so on. A to D, you have 2 edges. So you just fill in. Pretty straightforward. A pseudograph, not a simple graph. Okay, not a simple graph. So adjacent matrix can also be used to represent a directed graph. Remember, directed graph, you have arrow one way. The matrix for directed graph is G. VE has 1 in its example if there is an edge from Vi to Vj, where Vi, V2, Vn is a list of vertices. So in other words, if the graph is a matrix AG, which is a metric graph of Aij, then Aij is equal to 1 if Vi, Vj is an edge of G. So you have a edge between I to J, 0 otherwise. So the adjacency matrix for directed graph does not have to be symmetric, because there may not be an edge from Vi to Vj, where there is an edge from Vj to Vi. So remember, directed does not have to be symmetric. For the adjacency of a directed graph does not have to be symmetric, because you might have Vi to Vj, I and J. Remember, directed graph, you have arrow. You have from I to J, when they may not be an edge from I to J, sorry. J to I. When there is an edge from Vj to I, J to I, there has an edge, but I to J, there doesn't have an edge for that. To represent directed multigraph, the value of Aij is the number of edges connecting Vi to Vj. Similar with the undirected multigraph. So this is the just conclusion for undirected graph. Aij is 1 if Vij is an edge of G. Similar 1 if Vi Vj is an edge of G. This one can Vi V. For undirected graph, I to J or J to I. For directed graph, maybe I to J or J to I only, not the other way around. This makes it easier to find subgraph or to reverse graph if needed. So this is the adjacency matrix for UVW, VUW, VUW. It's supposed to be UVW, VUW. Doesn't matter, but just follow the order of alphabetical. I don't know why I put VUW. Never mind. So V to V 0, V to U, yes, you have 1, V to W 1, so on. Is this a symmetric graph, class? Is this a symmetric graph? Okay, correct. Just to see whether you are there or not. I can see from the physical class can like know whether you pay attention or but not the online class. But never mind. So this is pretty straightforward. Not the hardest part yet. So for the directed graph, you have from V to U. You have from V to U, yes. But from U to V, you don't have. U to V doesn't have. But you have from V to U. But not U to V. My U. Not U to V. So this is a directed graph. It doesn't have to be symmetric. Okay, let's go for the adjacency matrix of direct graph or digraph. So you have this graph A, B, C, and D. So you have here A, B, C, and D. A, B, C, and D. So A to A, no. A to B. A to B, no. 0. A to C, yes. A to C. And A to D, no. A to D. So B to A, yes, you have B to A. 1. B to B, no. B to C, 0. B to D, also 0. You have C here. C to A. There's a HC between A and C, but it's not from C to A. It's from A to C. So C to A, you put 0. C to B, C to C. So C is a termination point. It doesn't, there is no like initial or starting from point C. C is all termination point. C is termination point. That's why you can see the row, the column all 0. And D, you have D to A, D to B, and D to C. All right. So let's say if you have a directed graph VE with loops. So you have here 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let's see 3. 3 to 1. 3 to 1 you don't have. 3 to 2 you don't have. You have 2 to 3 but not 3 to 2. 3 to 3 you have 1. 3 to 2 you have 1. 3 to 3 you have 1. 3 to 4 0. 3 to 5 also 0. 4 all 0 except for 4 to 5 and 5. 5 to 1 you don't have. 5 to 2 you don't have. 5 to 3 yes you have. 5 to 3 not 3 to 5. 5 to 4 no. 5 to 5 also no. So this is a digraph adjacency matrix. Again, the adjacency is based on the vertex. Based on the vertex. If the vertex is more useful information rather than the edge, you use an adjacency matrix or neighbors. Now we go for the incident matrix where you use edges. Rather than graph, you use edges. So like the matrix of incident matrix of Mij, where Mij is 1 when edge Ej is incident with V1, 0 otherwise. Why is incident? Where H for the vertex I, they have H anywhere from vertex I. There is an H. Let's see how it. So you have here, okay, this is the incident matrix. E1, E2, and E3. So on the row you put VUW or UVW. UVW, E1, E2, and E3. Okay, UVW, U and E1. This one U and E1. Is there any incident? U does E1 H1 connect with U? Yes. H1 connect with E2? Yes. H3 connect with U? No, 0. Let's see the vertex V. Is V connect with E1? Yes. V connect with E2? No. V and E2 is not connected. V and E3? Yes. And W, is W connected to E1? No. W connected to E2 and E3. So you can see UVW, just don't use this because it's not alphabetical order UVW. So this one you can see pretty straightforward. When an HEJ is incident with V1 or connected incident, so U is incident with E1 and E2. So E1 and E2 you put 1. W is incident to E3 and E2. So E3 and E2, E2 and E3 you put 1. E1 is not incident with W, so you put 0. So this is the incident matrix. When the information of edges is more useful, you use incident matrix. When the information about vertex is more useful, you use the adjacency matrix. So again, here you have a V1, V2, V3, V4, and V5. You have H1, H2, H3, H4, H5, and H6. Okay, E6. So V1, is V1 incident with E1? Yes, you put 1 here. If V2 incident with if E2 is incident with V1, yes, incident, you put 1. If V1 incident with E3, no, 0. E4, no, you put 0. E5, 0. E6, also 0. So V1 only incident with E1 and E2. E1 and E2. Now you look at the second row, V2. Is V2 incident with E1? No, so you put 0. V2 incident with E2? No, you put 0. V2 incident with E3? Yes, V2 and E3, 1. V2 and E4? Yes, 1. V2 and E5? No, 0. And V2 and V2 and E6 incident, so you put 1. And so on. So this is the direct incident matrix for undirected graph. Simple undirected graph. Pseudograph and incident matrix. So again, you put on the row, you put a vertex V1, V2, V3, V4, and V5. E1, E2, E3, E4, E5, E6, E7, and E8. All right. So V1 is incident with E1, yes, a loop. V1 is incident with E2, yes. V1 is incident with E3, yes. V1 incident with E4, no, 0. E5, no. E6, no. E7, no. And E8 also no. So V2 is incident with E1 or not? No, V2 is not incident with E1. So you put 0 here. V2 is incident with E2, yes. V2 is incident with E3, yes. V2 is incident with E4, yes. V2 incident with E5, no. E6, yes. E7, yes. E8, no. So here you put a V2. So this for the incident matrix. On the row you put all the vertex. On the columns you put all the edges. How about the directed graph or digraph? This matrix is filled with 0 or 1 or -1. Okay, it's different for directed graph. 0 represent that the row H is not connected to column vertex. 1 represent that the row H is connected as outgoing H to column vertex. And -1 represent that the row H is connected as the incoming H to the column vertex. So let's see the example here. You have this, you have A, you have A, B, C, and D, and you have 1, 2, 3, 4. You have A, B, C, and D here. Again, it's same with the undirected graph. On the row, you put a vertex, and on the column, you put an edge. So A to A, 1. So A and 1, yes. 1 is represent the row edge is connected as an outgoing edge to column vertex. A, 1 is outgoing from A, so you put here 1. 2, is A incident with 2? No, you put 0. Is A incident with 3? Yes, but as incoming, you put -1. 4, as outgoing, you put 1. Let's see about, let's see the vertex B. Let's see the vertex B here. If B incidence with 1, yes. Is it outgoing or incoming? It is incoming. So if incoming, you put -1. Incoming to B is -1. Incident with 1, H1. But incoming, you put -1. If B adjacent with H number 2, yes. As outgoing, what is outgoing? You put 1. 1 and outgoing. 3, no incidence. 4 is no incidence. Let's see the vertex C. Let's see the vertex C. Is C incident with 1? No, put 0. Is C incident with H2? Yes. As incoming or outgoing? It's incoming. So incoming, you put -1. Incoming, -1. Is C incident with H3? Yes. Outgoing or incoming? It is outgoing, so you put here 1 because of the outgoing. C to A. Sorry, C C and H3 is outgoing, and so on. So it's a little bit more work you have to do for the directed graph or digraph. So this example of a digraph with loop. Say you want to D and E8. D and E8. Since D and E8 is incoming, so you put 1. D and E8. Okay. D E7 outgoing. D and B incoming. D and E7 is outgoing. So you put 1. Correct. E6 not incident. E5 is incoming, so -1. E4 is also incoming, so you -1. E3 is outgoing 1. E8 is also 1 because it is outgoing and incoming as well. So this is the loop D and E8 +1. It is considered incoming and outgoing, but we put +1. Consider it as a outgoing as well, because D outgoing to D. It is a little bit tricky, but you get the way. I hope that you understand this. I hope you get this. The loop in the digraph is equal to 1. D and E8. E8. D is incident to E8. It can be outgoing, incoming. So it's considered as an outgoing. D outgoing to D. So you have to put 1. So now is the isomorphism of graph. Isomorphism. So isomorphism, basically the graph can be, there's a different graph, but it can be represented as a similar graph. It is isomorphic. There is a 1-to-1 and onto function f from v1 to v2. You have a two graph. You want to see whether it is isomorphic or not. Whether it can be represented as the same graph or not. So you can see like graph isomorphism G1, where if there is a graph G1 where set of vertex 1 and set of edge 2 is supposed to be E1, not 2, okay? Never mind. So you have a graph 1 where set of vertex of graph 1 and set of edges of graph set of edges of graph 1 E1, and you have graph number 2 set of vertex 2 and set of edges 2 are isomorphic if there's a one-to-one and onto function f function from v1 to v2 with the property that a and b are adjacent in G1, and if and only if a and function b are adjacent in graph number 2 for all a and b in v1. Function is f is called isomorphism. So basically you have a two graph here. You have a graph two graph where a and b are adjacent, and function a and function b of graph number 2 is also adjacent in G2 for all vertex a and vertex b in V1. So one of the application you can think of is in chemistry to find out compound have the same structure, organic chemistry. Okay, now you have U1, U2, U3, and U4. And you have V1, V2, V3, and V4. Solution, the function f with FU1 is V1. FU1 is similar to V1, function U1. Function U2 is similar to V2. Function U2 is similar to V4, sorry. Function U2 is similar to V4. Let's see if you look at this graph. If you like you what we call that if you move this V1 and V4 here, V3, V3, V4, this is V3 and V2, but you move V1 and V4 here, V1 you move here and V4 you move here, so you have your V1, V4, V3, V2, V1 and V3, V2 and V4. Let's say you move V1 here. From here, you move outside. You move down to bottom of V3. Then you have a similar, or we call that isomorphism. This graph is isomorphic. Graph G and graph H. And you see that U1 is equal to V1. Yes, U1 and V1. Doesn't matter. U2 is equal to V4. U2 is equal to V4. And so on. U3 is equal to V3. And U4 is equal to V2. So you understand the isomorphism. Basically, you want to see whether this graph is similar or not. Can be represented as a similar graph or not. Is the graph isomorphic? If the graph isomorphic or not, you have to investigate whether each vertex is similar. Vertex of graph number 1 is similar to vertex of graph number 2, and so on. And you also can investigate with the adjacent vertices of G are U1 and U2, U1 and U3, U2 and U4 and U3. Each of the first function U1 is equal to V1, function U2 is equal to V4, function U3 is equal to V3, and so on. So this is similar. Let's say you move V3 here, you move V3 from here to here. So still you can have a nice square graph, a similar graph. If you ignore the geometry or the scale of it, doesn't matter what is the length of U2, U4, U1, U2, U1, U3, and so on. So isomorphism of graph is difficult to determine whether two simple graphs are isomorphic using brute force because there are n factorial possible one-to-one corresponding between the vertex set of two simple graph with n vertices. Let's say you have 1000 vertices. It's very difficult to determine whether it's isomorphic or not. The best algorithm for determining whether two graphs are isomorphic have exponential worst case complexity in terms of number of vertices of the graph. So there is no yet a formula to identify the isomorphism of graph. Okay, there's no solution yet. Exponential worst case. Sometimes it's not hard to show that two graphs are not isomorphic. We can do so by finding a property preserved by isomorphism that only one of the two graphs has. Such a property is called a graph invariant. You can see a graph invariant. If you see a two not similar, you can say that this graph is not isomorphic. We will see on the example, later example. There are many different useful graph invariants that can be used to distinguish non-isomorphic graphs, such as number of vertices, number of edges, and degree sequence. We will encounter others in later session of this chapter. So the isomorphism of graph, let's say like 2000 vertices or 3000 vertices or more vertices, very difficult. You have two graph that have more than 1000 or many vertices. There are no solutions yet. Maybe you can invent one. So this is still open for to solve. But you can investigate others like the number of vertices, whether there is the same number of vertices, a set of neighbors and stuff. Okay, like number of vertices, number of edges, and degree sequence. Let's say this you want to check whether graph G and graph H whether they are isomorphic or not. Both graphs have 8 vertices and 10 edges. So check on the vertices is correct. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 vertices and 10 edges. You have a 1, 1, 2, 3, 4, 6, 7, 8, 9. 1, 2, 3, 4, 6, 7, 8, 9, 10. Not 10 edges. 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 edges. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 6, 7, 8, 9, 10. So both have 10 edges. They also both have 4 vertices of degree 2. Remember degree 2. 4 vertices of degree 2. So you have here A, 1 degree 2, B. No, sorry. You have C, degree 2. You have G, degree 2, E, degree 2. 4 vertices of degree 2 and 4 degree 3. So this one have 4 vertices degree 1, 2, 1, 2, 1, 2, and 1, 2. And 4 of degree 3. 1B, 1 to 3, F 1 to 3, H 1 to 3, and D 1 to 3. So this one as well, S, W, Z, and V all have 3 degrees. However, G and H are not isomorphic. Note that since degree A2 in G, if degree A2 in G, a mask corresponding to TUX or Y in H. But these are the vertices of degree 2. But each of these vertices is adjacent to another vertex of degree 2 in H, which is not true in G. So you can see here degree A is 2, but corresponding to TUX or Y in H, because these are vertices of degree 2. But each of these vertices is adjacent to another vertex of degree 2. So like A and C must be adjacent to another vertex of degree 2, but A and C here is adjacent to vertex that have 3 degrees. C as well, but this one you have, if you see on the T, this is degree 2, degree T is 2, but it adjacent with degree U, which have degree 2, it's adjacent to vertex U that have degree 2, but it also adjacent to the vertex S as vertex S that have degree 3. If you see G here, each of the vertices that have degree 2 is adjacent only to vertex that have degree 3, but not in the case of H, where you have one neighbors that have degree 2, one neighbors that have degree 3. So this is one way for you to check whether it is isomorphic or not. So it is if the number of vertex of edges are small, it's easier. But when it's like large number of vertex or large number of vertices, it will become more difficult. So alternatively, note that subgraph of G and H are made of vertices of degree 3 and edges connecting them must be isomorphic. But the subgraph as shown in the right are not isomorphic. So this is a subgraph which is not isomorphic. Again, determine whether these two graphs are isomorphic. Both graphs have 6 vertices and 7 edges. They also both have 4 vertices of degree 2 and 2 of degree 3. You can check. The subgraph of G and H consists of all vertices of degree 2 and edges connecting them are isomorphic. So it is able to try to find isomorphism of F. So this graph, you can check the function of U1 is equal to V6. Function of vertex U2 is equal to V3 and so on. So this graph G and H is isomorphic. Okay. Showing that this corresponding position of H is straightforward, so we will omit the F is an isomorphism because the function is isomorphism. G and H are also isomorphic graph. Okay. It passed the number of vertices and number of edges, passed the vertex degree as well, and also it passed a function. The subgraph of G and H consists of all the vertices of degree 2 and the edges connecting them are isomorphic as well. So of all vertices of degree 2, 1 and 2, 1 and 2, 1 and 2, the subgraph. Also, of course, this also a subgraph of degree 2, 1 and 2, 1 and 2, 1 and 1 and 2, 1 and 2. So this graph G and H can be represented as a similar graph or isomorphic graph. So what is the application of a graph isomorphism? Chemists use a molecular graph to model chemical compounds. So vertices represent atoms and edges represent chemical bond. When a new compound is synthesized, the database of molecular graph is checked to determine whether the graph representing the new compound is isomorphic to a graph of compound that is already known. Electronic circuits are modeled as a graph in which the vertices represent components and edges represent connection between them. So the verification that a particular layout of circuit according to its design original schematics, determining whether a chip from one vendor includes the architectural property of another vendor. So you can check whether if you have electronic circuits, which is more related to us. The verification that a particular layout of circuit corresponds to the design original schematics. You can check the isomorphism, the graph isomorphism, and whether chip from one vendor includes intellectual property of another vendor. So this is also you can check whether a competitor copying you or not. If you have patented it and the competitor copying you, you can sue them. So you can use the graph isomorphism to check whether the intellectual property has been copied or not. Do you need a break? Everyone, are you still with me? Yes, doctor. Okay. So we have a break about 10 minutes. Then we continue back to 10. So this is the second part, a connectivity in the graph. So you have a path and you have a connectedness in undirected graph, connectedness in directed graph, and counting path between vertices. So path, route, some books say route or whatever is the edge. A path is a sequence of edges that begin at vertex of graph and travel from vertex to vertex from vertex to vertex along edges of the graph. As the path travels along its edge, it visits vertices along this path. That is the end point of this. So basically, you have vertex A, vertex B, vertex C, vertex D. So you travel from A to D. Your source, your destination is D, or vice versa. So this is the path from A to D. Path AB, path BC, path AB, BC, and CD. AB, BC, and CD. Applications. Numerous problems can be modeled with paths formed by traveling along edges of graphs, such as determining whether a message can be sent between two computers, network, efficiently planning route for mail delivery, or even your Google Map ways also use a path like minimum path or fastest route, shortest distance and stuff. So definition, just don't worry about the definition when you do the example. It's okay. Wording in mathematics just make you more confused or something. So let n be the non-negative integer n, and g is an undirected graph. A path of length n from u to v in G is a sequence of n edges from E1 until En of G, which there exists a sequence of XOU, X1, Xn minus 1, Xn, and V of vertices that Ei edges I has for I equal to 1 until N, the endpoints of Xi minus 1 and Xi. When the graph is simple, we denote this path by vertex sequence XO, X1 until Xn. The path is a circuit if begins. So if it's simple, we know this path the vertex sequence x0 to xn. Since listing of the vertex uniquely determine the path. So a graph is simple like A, B, and C. Vertex A, B, and C. So this is a simple one. The path is a circuit if begin and ends at the same vertex. So you have A, B, C, and D. So start from A, B, B, C, C, D, and D, A. So this is a circuit, a loop or something like that. A circuit. No, loop, you don't confuse loop with going from the same vertex, terminate at the same vertex as well. So you just like the same source and end at the end point. Source is the same A, go back, go to B, BC, CD, and DA. So this is circuit. The path of circuit is said to pass through the vertex x1 until xn, traverse edges e1, e2, en. So you have e1, e2, e3, and e4 until en. A path of circuit is simple if it does not contain the same edge more than once. So this is a simple. Only one edge, only one contains same edge more than once. So A to B only one time, B to C is only one time E2, C to D only one time E3, and D to A is only one time E4. Does not contain the same edge more than once. So this terminology also is true for directed graph. Undirected and directed graph basically have a similar meaning. You have a simple, you have a circuit, and so on. Okay, let's say path in the simple graph here. A, B, C, D, E, F. Okay? Why is it simple? Because it doesn't have multiple edges and doesn't have loop. So A, D, C, E. Okay, we look at example number 1. A, D, C, F, E is a simple path of length 4. A, D, A, D, C, F, and E. ADCFE is a simple path of length 4. AD1, DC2, CF3, and FE is 4. The path length is 4. 1, 2, 3, and 4. Okay, let's see. How do I handle it? So let's see example number 2. D is C is not a path because E is not connected to C. D, starting from D, E, C. There is no connection from E to C, so this is not a path, correct? BCFE is a circuit of length 4. BCFE. Okay, use a different color. B, C, F, E, and B. So 1, 2, 3, 4. BCFE is a circuit because start at B and at B. It's a circuit of length 4. 1, 2, 3, and 4. Length 4. ABDAB is a path of length 5, but it's not a simple path. So ABEDAB. We delete this. Sorry. Never mind. I recorded this lecture, so I will upload on the YouTube later. So ABEDA, ABEDAB, ABEDAB. Is a path of length 5. ABEDE. ABEDAB is a path of length 5. 1, 2, 3, 4, and 5. But it is not a simple path. Why? Because it has gone through path A and B twice. AB and AB again. AB and AB again. So it's not a simple path because it has gone through the path AB twice. So a path sequence does not contain the same edge more than once. So A and B has been passed through 2 times, so it's not a simple path. It's just a path, but it's not a simple one. So a path is a sequence of edges that begins at the vertex of a graph and travels along edges of the graph. So you have a graph of G with a set of vertices V and edges E. Path P represented from U to V. U to V, you go U1, U1, 1, 4, 4, 5, and 5V. U1, this one U1, 1, 4, 4, 5, and 5V. Okay? 1, 2, 3, 4. Length 4. 1, 2, 3, 4. Okay, degree of separation. Path in acquaintanceship graph. In an acquaintanceship graph, there is a path between two people. If there is a chain of people linking these people, where two people adjacent in the chain know one another. In this graph, there is a chain of 6 people linking Kamini and Ching. So let's say Kamini and Ching. 6 people. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 1, 2, 1, 2, 3, 4. Yeah, it's F. 1, 2, 3, 4, 5, and 6. Between Kamini and Ching. In this graph, there is a chain of 6 people linking Kamini and Ching. So you can visualize this as your Facebook, okay? Degrees of separation or acquaintanceship graph, like your Facebook or whatever, LinkedIn, whatever social media, Instagram. So some have speculated that almost every pair of people in the world are linked by a small chain of no more than 6 or maybe even 5 people. The play 6 Degrees of Separation by John Gore is based on this notion. You can, of course, you can watch these movies. Erdos number. In a collaboration graph, two people A and B are connected by path when there is a sequence of people starting with A and ending with B, such as the endpoint of each path are people who have collaborated. Okay. In the academic collaboration graph of people who have written papers in mathematics, the Erdos number of person is M is the length of shortest path between M and the prolific mathematician Paul Erdos. So let's say I collaborate with with Dr. Badrul Anwar. So I have a collaboration with Dr. Badrul Anwar. So I have a collaboration graph. Okay, you can use Erdo numbers to model that. Bacon numbers. In Hollywood, two actors A and B are linked when there is a chain of actors linking A and B, where every two actors adjacent the chain have acted in the same movie. So in Hollywood, they have this Bacon number. It's not like this is not a this is not a kind of a meat from pig. The Bacon number is from the actor Kevin Bacon. This is a old school. This is a old school actor, not a new one. So Bacon number of an actor C is defined to be length the shortest path connecting C and the well-known actor Kevin Bacon. So note that we can define similar number replacing Kevin Bacon with different actor as well. So in Hollywood, they have this Bacon number. Some model a Bacon number. So you can also use this is a connectivity graph. Connectedness in undirected graph. An undirected graph is called connected if there is a path between every pair of vertices. An undirected graph that is not connected is called disconnected. Okay? An undirected graph is called connected if there is a path between every pair of vertices. Like you want to go to A to E is connected. You can use either this. There's a number of connection. Let's say you want to A to E. You have A, B, E, C, D, E, or you also can use A, C, F, A, E, and or A, E, A, A, E, A, C, D, and E. So you have a connected. And under the graph that is not connected is called disconnected. There is no like path from A to F or A to E. So this is called disconnected. We say that we disconnect a graph when we remove vertices of edges or both to produce a disconnected subgraph. Okay, let's see on the example, this one G1. Here is the graph G1. It's connected because there is a path between any path of vertices. So any path of the vertices is in graph G1 is connected. You can go from A to D, E to B, G to B, G to A, and so on. However, G2 is not connected because there is no path between vertices A and F, for example. So this is a disconnected, not connected or disconnected. So connectedness is an undirected graph. An undirected graph is connected if there exists a simple path between every pair of vertices. There exists a simple path, not if. An undirected graph is connected if there exists a simple path between every pair of vertices. So in this example, graph G of set of vertex V and set of edges E is connected since for V1, V2 until V5, there is a path between Vi and Vj. Vi and Vj. V1, V4, V1 to V5 and so on. There is a path between Vi and Vj where I is less than I and J equals I less than 1 less than I and J less than 5. Connected components. A connected component of graph G is a connected subgraph of G that is not proper subgraph of another connected subgraph of G. Okay, again. So connected component of graph G is a connected subgraph of G that is not proper subgraph of another connected subgraph of G. A graph G that is not connected has two or more connected components that are disjoint and have G as their union. So let's see on the graph H here. The graph H is the union of three disjoint subgraph H1, H2, and H3. These three subgraphs are the connected components of H. So C can become D and E can become H as well. So this is the connected components of H. Connectedness in directed graph. A directed graph is strongly connected if there is a path between from A to B and path from B to A whenever A and B are vertices in the graph. Okay, you have a strongly connected and you have a weakly connected directed graph. There is a path between every two vertices and the underlying undirected graph. So you assume like this directed graph is like undirected graph. Okay, let's see the example. Okay, let's say this one, G1. Let's say this A, B, and C. A, B, and C. A, B, and C. So example, G1 is a strong component. Why? From A, if you want to go to B, you have AC, CB. From C, you want to go to A, you have CB and BA. From B, you want to go to A here. If you want to go to C, BAC. So there is a path of each vertex to go to each of the vertex. So this is called a strong component because you can go from B to A, B to C, A to B, A to C, C to B, C to A, everything. Any graph. This is undirected. Okay, G2 is a weak component. Why? If you want to go to A to B, yes, A to C, yes. Let's say you want to go from C to A. You want to go to from C to A. There is no path between C to A because C to B and CAC is one way. So there is no path C to A, no path from C to A. But if you remove the arrow here and it's put an underlying, you assume this as an undirected graph like this, there is a connection between each of the vertices to any of the vertices in the graph. So this is a strong component of directed graph. This is a weak component of undirected graph if there is a underlying undirected graph that can model the directed graph. See again. A directed graph is weakly connected if there is a path between every two vertices in underlying undirected graph. So if you convert this directed graph to undirected graph, you can see that all the vertices have a way to reach other vertices. But if it's a directed graph, there is no connection from C to A. Okay, from A to C, yes, but not from C to A, or even B to A. B to A also doesn't have a connection. Again, we look at C. G is strongly connected because there is a path between any two vertices in a directed graph. Let's say you want to go to A to D, you can go to A, B, D. Or A to E, you can go here. E to C, you can go E to C here. E to C. This is a strong component. G is strongly connected because there is a path between any two vertices in a directed graph. Hence, G is also weakly connected. The graph H is not strongly connected since there is no directed path, but it's weakly connected. So if G is a strong connected, G also is a weakly connected. I know it's a confused, but this is a definition from the textbook. If G is a strongly connected, it also can be a weakly connected. H is not strongly connected since there is no directed path from A to B. Let's say I want to go from A to B. There's no way I can go from A to B, only B to A. But if you remove all this arrow and you assume it as an undirected graph, there is a connection from any of the vertices. So the connected component of the web graph. So you have a web graph page that can be reached from page in the GSCC but do not link back. Page that link back to the GSCC, a giant strongly connected component. Also a web page, a www or web page, all the www or web page. You can model it using a component of web graph. Counting path. Isomorphic graph must have the same path. If one is a simple circuit of length k, then so must be the other. So there's a theorem for that. Let M be the adjacency matrix of graph G. Then each ij entry of M to the power of R is the number of paths of length R from vertex I to vertex J. So let M be the adjacency matrix. Adjacency matrix use what? Vertex. Remember? Adjacency or neighbors matrix use vertex. Incidence use H. So M be the adjacency for graph G. Then each ij entry of M to the power is the number of paths of length R from vertex I to J. Meaning that if you want to find how many paths of M that has the path length of R. Okay, how many? The path length of R. So then each ij entry in M to the power of R is the number of paths of length R from vertex I to vertex J. That's the standard power of M. This is standard power of M, not a Boolean product. A standard power. Normal one, not a Boolean. So you have here counting how many paths of length 4 are there from A to D in graph G. So if you do the adjacency matrix here, A, B, C, and D, A, B, C, and D, you have here this adjacency matrix. So from A to B, A to C, A to B and C, A to A no, A to D no. So you have the adjacency matrix of G. You want to find how many paths of length 4. So you have to put A to the power of 4 based on this theorem. Then each identity of M to the power is the number of path length R from vertex I to vertex J. So path length 4. Path length of 4 there from A to D. So you have to do a matrix multiplication 4 times. This matrix is to the power of 4. So you get A to the power of 4 is, say we can use MATLAB or whatsoever. Here you have 8. Since the number of paths of length 4 from A to D is 1 over 4 entry of A to the power of 4. So you have A to D is A, B, C, D, 1, A, B, C, and D. So you have 8 paths, path length of 4, 8 paths. A, B, A, B, D, A, B, A, B, D, A, B, D, B, D, A, B, D, B, D, A, C, A, B, D, A, C, A, B, D, and so on. So this is the counting path of vertices. So that's it for today.